I'm Alberto, and together with my colleagues that I will introduce shortly, we will present this tutorial on how to integrate and interact with a federated network of rare disease resources. Through this presentation, you will sometimes find QR codes. So some of them are only additional information in case you are interested and want to check more, or you have questions, you can check them out. And in other cases like this one, there are links to the presentations themselves in case you want to follow along. First of all, in case you are not connected to the Wi-Fi, you can do so using eduroam if you have access normally, or you can use the Fletcher or KPN network for your from the hotel. I will give 1 minute so that everyone is connected. If anyone has any questions or problems with the presentation, we have the Slack channel open on this other laptop, and one of us will always be monitoring it, so we can answer your questions there, but we will also have a turn of questions for the people present here, of course. Yeah, if you have questions during the presentation, you can tell us, you can raise your hand and we will answer them, but you can also ask through Slack, whatever you prefer. So I hope everyone is connected to the Wi-Fi and there's no problems with that. So I also wanted to point out that there is a follow-up hackathon on the last day of the conference for this tutorial, where we will go more in depth on how to do the things that I will teach today. And we welcome you there, and we hope to see you there with us. So first of all, I wanted to give an introduction to the tutorial. Sorry. First, we will have an introduction to what this looks like once you are done, what you can achieve with these technologies. That will be my colleague Cesar. Then we will give you a quick tutorial, a quick introduction to one of the technologies that we use, that is called Fair Data Point. That will be my colleague Warmar. Then we will have a coffee break of 20 minutes so that we can rest a bit. Then I will give a quick, well, not quick, demo on how to programmatically or not interact with the Fair Data Points. And then my colleague Pablo will give a demo on how to use the Clinical And Registry Entries Semantic Model, which was designed to model patient data.
Cheer you up a little bit after the very good lunch we had. I know I can see some sleepy faces. I would ask you to join this Mentimeter. You should be able to see now the code that you can use to access it. So you just enter on menti.com and you use the code 63886283 to access this Mentimeter. So the first question we ask you is to understand your background, because depending on the background, you adjust some parts of the tutorial accordingly. I think most importantly that we want to know is if you have a technical background or you're more on the, like, for example, domain expert side. Well, you can already see that we have a very diverse group in here. People from bioinformatics, pharmaceutical sciences, public health, computer engineering, computer science. Yeah, this was more or less what we expected, right? Like to have a kind of a mixed group, which is good. So let's move to the next question. This is annoying. So have you heard of the AGPRD's virtual platform before? Interesting. Half of you have heard of the virtual platform before. Still true. And half of you haven't. That's good because we have an introduction about the virtual platform. And the next question, oh no, it's not a question. So for those who haven't heard of the virtual platform before, it is a growing network of fair resources ready to serve the rare disease research community, and it includes catalogs of resources, especially patient registries, biobanks, and knowledge bases and tools focused on rare diseases. There is a difference that you should be aware. So there is the virtual platform, which is the background network that runs connecting all the resources. And there is the VP portal, which is the user interface, one of the user interfaces, I would say, that allows you to search and query on the virtual platform network. This is how the user interface looks like. I will quickly show a demo in a few minutes, but you can see here that you have like a description, some external links to tools and resources, and the most important part is the search bar. Let's say that you can query for resources related to your interest. One thing that I would like to know, so you can grab your phone again to answer this one, is what do you think when you hear about a virtual platform? Like, especially for those who just heard about it. What comes to your mind when you hear about it? Okay, okay. So maybe it was the problem with the question. Or you don't like the name. You don't like the name. Okay. Maybe we should call it Alberto. It will be more practical. Yeah, right? What's the Jiki domain agnostic? I like this. Let me see. So yeah, so now that I know a little bit your feelings about the virtual platform and about its name, I will show you a quick demo of the virtual platform. And for that, you should be aware that it allows for different types of querying. So you can query the virtual platform by, for example, the name of a disease, by an ORFA code, by an ICD-10 code, OMIM code, gene name, or by HGNC number. And for the demo, we will use the ORPHANET rare disease ontology, which is a structured vocabulary for rare diseases derived from the ORPHANET database. I see that you're nodding, so I'm correct. Yeah, it captures the relationships between disease, genes, and other relevant features. And for the demo, I will use this specific disease, osteogenesis imperfecta, which is listed as in the Ordo ontology with the code ORPHANET 666. Is easy to remember. Dangerous, but okay. And you see that, well, in the ontology, you see the disease name, the code, human readable definition of the disease, but also some synonyms like brittle bone disease, glass bone disease, and etc. So let me try to change. How do I change the screen here? For the fast. Okay. I have to hold the microphone and type. So to show you the power of the virtual platform, I will start just first by typing the name of the disease. So we have osteogenesis. So by typing the name of the disease here, you see lots of synonyms, but well, I found the one I want to, osteogenesis imperfecta. And when you search for it, you get all the resources that contain information in some way about osteogenesis imperfecta. But if you, yeah. I'll get there. Yeah. But thanks for asking. Yeah, so as you could see, at first got the results by performing a natural language search. Like I used the name of the Osteogenesis imperfecta. Oh, I deleted, but we had 21 results before, trust me. But if I try to type the code, I also get the answer. Also by typing the code, so I can make it more precise, let's say. And if you sum here, you get 21 results. I hope I did the correct math. But also, if I redo this search and I use the synonyms that I mentioned before, for example, brittle, I think it's 2 T's, brittle bone disease, I'll get the same results, 21 results with the same disease code. So this allows for a very, let's say, semantic research query, because we can search for the name, for the code, for the synonyms, and we get the very same results. Just one last demonstration. I can use the other synonym, glass bone disease, and again, you get the same results. I want to open another tab. You have the disease here, osteogenesis imperfecta, and the description, the synonyms. But as asked, this is an umbrella term, and you have more specific types of osteogenesis imperfecta. For example, osteogenesis imperfecta type 3, which is one of the subtypes of the 5 subtypes of osteogenesis imperfecta. And if you want to be more specific, you can use the Ordo's ontology classification. Like here, I was performing search using the most generic term. And let's say, for example, I want to be more specific and I want to search for the osteogenesis imperfecta type 3. So you see here that it has a code, a bigger code, 216812. And I can come here and, well, first I can type osteogenesis imperfecta type 3. And you should have, and you get the results from your more specific query. And if you compare, like, for example, here you have BBMRI showing that you have resources, for example, in Italy, Spain, and Italy again. And if you compare to the ones here, you see that the Italian, the Spanish, and again, the Italian ones are here. So the bigger umbrella query also covered the more specific ones. And as I mentioned, just to prove, I will type the code here again. And again, you get the very same 3 results. Another thing that the virtual platform allows you to do is to filter your research also using semantic filters. So let's say, for example, here, when I filter the research, you can select for the resource type, the countries associated with the results, and also some parts that are more specific, such as like sex, age this year, in case of patient registries, age at diagnosis and symptom of onset. We should have logged in before, but I forgot. But just to give you an example, like let's say, for example, you want to just have registries in Italy. So Claudio is happy. And you can also perform such kind of filter, and then you get all the resources that are from Italy. So it allows to search for different resources in different ways, and it tries to have very precise results because we are being supported by ontologies. It also includes data and privacy protection concerns because in the virtual platform, the data remains at the source level. Like we are not copying data from, example, Italy to the Netherlands. We are querying data at the source, which it's a good solution, like, for example, to comply with the GDPR compliance and other privacy concerns. I think this is the last slide of my introduction. And now, after this short and quick demo, I want to know from you, what do you think the VP would allow you to do in the context of your research? Nothing is also an answer. And then Alberto will show you how you do things with the VP.
Maybe also to give is this working, microphone? Yeah. Okay. So to give some context to what I think is context to this question, and maybe we should have phrased it as, what do you think the virtual platform should allow you to do? One thing is that last year, Alberto, who was also at the table here, gave a talk, which was based on a survey among rare disease data providers, to put it way. It's a bit more complicated than that, but let's call them providers. And they were all they indicated in the survey that they were eager to share their data with research communities. And here we have a data research community. And we sort of provided the technology, the means by which that can be enabled. And now if you read it as what should it allow you to do with these types of technologies, then I guess a lot of things that you said will be for us incentives to go back to those providers and tell them, we have the technology to do this. If you provide your quality data, because there is some quality data there, then these kind of questions can actually be answered. Because in a lot of cases, they don't really get that. So if we have those questions on the list, then we can say, look, this kind of community can do this kind of these things for rare disease patients with this type of technology. So in a way, your comments were all very valuable, because that is what we can go back to our data providers. And by the way, we're working at the Leiden University Medical Center. We're one of them. We're one of those providers. So also in our own house, we're going to use this. Say, yeah, we need to do this. Yeah. And also please type it in, because then we have it on record.
Because actually there is an inherent problem in data providers here. So I happen to can be data provider. I spent 20 years cross-Atlantic failing to give the most relevant information for fine-tuning of the treatment. Unfortunately, not diagnosis of my kid. It's not there, so you cannot be provided. Only I can. I have this data. It's on the cloud. I give it peer-to-peer to doctors, and so on. So if you talk about rare diseases, I mean, I know it's a little bit complex. It requires a lot, but you will include patients as providers. It doesn't need to go to electronic health record. It never goes, for many reasons. I think wrong reasons, but so another idea. For research, of course, and you get it for free. We'll pay for you, like not the other way around.
All right, thank you. So I'll sit down so I don't injure my neck. I had a long flight and early, so please bear with me. This is only slides, not interactive, but if you have any kind of questions, you can stop me and I will try to answer. So this is the metadata part that someone alluded to, that this would be it, the central part of the platform. This is a system called the fair data point, and it's a specification and also reference implementation. But there are other implementations of the same specification as well. So the example here is going to illustrate some of the the structure that kind of ties the virtual platform together. It's going to be generic in one sense, but we're going to go into some examples of how it's been configured to address some of the aspects of the virtual platform in the rare disease case. So the first part here is to address, so how do we make these rare disease resources machine actionable and fair? So that's findable, accessible, interoperable, and reusable. I'm not going to go into any fair metrics or assessment, but just to illustrate the point here, and let me try to move this. So we will incrementally need more common agreement across the different resources as we want to do more advanced things. I mean, we do need some shared expectations on what interfaces we can use, what kind of standards people have used across the different resources, and what kind of queries that you would be expected to be able to do. If that includes genomics, for example, or other omics in addition to patient information. So there are a lot of use cases that have been collected in the European Joint Programme for Rare Diseases, and some generic ones is resource discovery, just finding out which resources have the type of data that I'm looking for. And I think that's where a lot of those resources that we discovered are at. So you can search for disease and maybe some other parameters to see so which resources exist. And for this, we need, for example, this common metadata service, and then a schema that kind of says these are the kinds of terms that you should be able to query all of the resources on. And then as you go further and might want to do some content-based discovery. So let's say you want to find the resources that match certain criteria on the number of patients with a certain diagnosis or something on those lines, then you would need some more common agreements. And in the European Joint Programme for Rare Diseases, they have implemented parts of the Beacon version 2 interface to address some of these queries that would not be considered sensitive in all cases. So you might be able to do that without having to log in, or with maybe less restrictive means of login. And there's also a specification for more expressive queries called care-SM. And I'm not going to go into that because it's going to be covered later. And then we have data analysis. You might want to do, run queries on the actual data themselves. And then you're into the territory that this is sensitive data, and you might need some sort of direct agreements, and you need to validate the kind of research question you're doing to the ethical permits and so forth. And here you might consider that, so there might be some Sparkle endpoints that should accept queries formulated using the care-SM, and those will be translated to the backend model that they have at the different resources, which would require some compute and maybe translation between the platform's way of phrasing things and the responses that you would expect to get back through the interface. And then you could also envision the full Beacon version 2 interfaces being implemented and combined with the care-SM, this model, and then perhaps also containerized compute. So, I mean, as long as you can agree on some shared specifications and a way of exposing what's available for querying across the different resources, I mean, you have endless potential. And then there's a lot of work in trying to organize the data to make sure that it's consistent, and the legal stuff, making people feel comfortable with providing access or exposing that you have certain kinds of information. But before I go into the nitty-gritty details of the platform, there are some prerequisites here, and I'm not sure to what level everyone is familiar with the RDF way of expressing things and the turtle representation that I'm going to use on some of the slides. So just very briefly to summarize, so RDF is a way of describing an object or a subject, which in these cases are going to be a URL of some sort or a URI. And then you have a predicate or a property that describes some element of that thing and gives it a value or an object in this case. So everything is in triples in the RDF way of thinking. So you have the subject, some sort of relationship, and then you have a object that kind of defines, so what would that mean for that specific subject. And then there's a representation format called Turtle that I'm going to use in the slides because it's pretty concise. So when you write these triples, and I will follow this convention of using a kind of indentation in the following lines. The first one here will contain the identifier for the subject, and then there will be the predicate here, and then you have the object at the end. So I mean, you can consider this to be the subject, and then you have a set of different aspects that I'm defining here. And the virtual platform, if you look at it as kind of this portal part, and then you have all these resources that might need some sort of adaptation or an adapter locally to interact with the platform. And the different levels that I described before, they are visible here as well. So you might have at the level 1 resource discovery, level 2 content discovery, and level 3 data analysis. And all of these can be implemented to different degrees depending on which resource you are. So not everyone will be on the same level. And I think no one is on level 3 at the moment. There's experiments going on in that sphere mostly. And looking then at what makes this metadata service tick, we have the data catalog vocabulary. And I'm going to digest this a little bit for you and describe how that can be adapted, restricted to make it more useful, and then adapted to specific use cases. So this vocabulary is very generic and is supposed to be able to represent more or less whatever kind of data catalog structure that you could envision, which makes it very flexible and very useless at the same time. So to make it useful, I mean, if you don't want to design a software that could address all of the different kinds of variation, you need to impose some restrictions. So creating profiles of this is what you usually do. So keep that in mind, that I mean, the parts here that I'm going to showcase are ways of describing services, catalogs of services and data sets. And then data sets, they also have something called distributions, which is basically a way of getting to the file or a version of the data set that is ready for consumption. And I've extracted some design features from the specification here. So, I mean, it's based on RDF, and it's based on the, it's supposed to allow discovery and support federated search. And the one of the primary objects is the catalog. And I have an example here to the right, which is serialized in this turtle format. And I don't expect you to read through all of these. There are many properties that are suggested that you can use in the DCAT standard. Very few of these are actually required. So I have highlighted a few of these that I think are just good examples of the interlinking between these different types of objects. But in essence, a catalog is a collection of metadata about different kinds of data sets or services. And it's in itself also a data set. So a catalog is a data set. A data set is something more generic called a resource. And this is made this way to intentionally allow it to be extended to other things. So you could have different standards or semantic artifacts or some other type of object that would be necessary to share with your resources. And then there's the data set, which is a conceptual identifier or description of the data. It's not the actual representation or the file itself. So this is supposed to be something that you could make available in different formats. And one of the formats could be a direct download of the entire file, and that might have some conditions. And another one could be a service that allows you to query and just extract some views or parts of the data set. And this is described using different kinds of distributions. And in the example here, I have used a distribution which is a direct download URL, and then a additional link then to another type of distribution, which I will expand a little bit on the next slide. So just keep in mind that the data set relies on the distributions to make the actual data available. And that's a good thing. And the distributions themselves, they can vary in different ways. So it could be just the same content, but in different file formats, or it could be in different languages if it's linguistically kind of related, or it could translate across vocabularies if you need a certain, like you need the ORFA codes for the data for it to be easy to integrate with some downstream analysis. Maybe that could be a version of the data that you're downloading. What you can see here is, again, the example with the download URL, but then you also have an example with instead referencing a access service and a access URL, which can be inferred using the vocabulary that has been defined as the standard. So when you describe the data service here, which could operate on a specific data set and just give you views or versions of that data set, or it could be more of a function. So you would send it data and then it would produce some output. So that's why you can register it under a catalog. Maybe it's more of a kind of data or a function where you send it data and you get a visualization back. But if you tie it directly to a distribution, then it might be more you're looking at this specific data set and getting certain views of that specific data set. So there's different ways of tying these data services to it. And then it's important to have some sort of access to the service online, since this is supposed to be for web services. And then some description of what the API looks like. And a suggestion is to use certain kind of machine readable or actionable API definitions. So that it could be a way of automating that part a little bit. So that frames the what is the data catalog and vocabulary part. And the more interesting part is how this is used in the FAIR data point, because the DCAT vocabulary in itself doesn't have a representation and it doesn't have any protocols to actually interact with it. So you could describe your data collection and all your data services and serialize this as a turtle file and send it to someone, and they could import that in their system, and then you could see, so all of these data sets and all of these services are available across those resources over there. But it's a lot more efficient if you could have this served over a standardized API, and that's what the FAIR data point adds to the DCAT vocabulary. So it includes, or it also expands a little bit, restricts the space of exploration for interacting with a DCAT-based catalog as well. So since it's designed based on this FAIR data point structure, it has some sort of description of what version you're adhering to, and it also gives you the opportunity to describe a schema for your entire system. So that's not included in DCAT. That's a OWL-based kind of open world kind of definition. So if you want to be able to do restrictions and really have some syntactic level power, you need something to add to this. And that's why we have this part here, the FAIR data point, and then the metadata service. So you know that there's an access point and it follows some certain rules, and then you can discover those schemas and those adaptations that you might have done to your FAIR data point. And then you know that there's always going to be a catalog at the top that contains all of the records that you might want to look at. So it kind of gives you an entry point to this vocabulary, and it also enforces some mandatory attributes as part of the base installation. The current specification is in 1.2. It still says in the specification that it's a work in progress. So I guess keep that in mind. It's not a W3C supported recommendation as with the DCAT vocabulary, but it's still very useful. And I mean, there is a reference implementation that you can spin up and just play around with if you want to see how something based on DCAT could work and how you could, I mean, put that in action in a similar way as we've done in the virtual platform. It gives you this serialization as a standard. You have Turtle, it's always going to serve Turtle and JSON LD. Turtle is going to be the default, and then you have the entry point. You know it's going to be a catalog that contains all of the records that you want to navigate through. You have the schema validation, and then there's also a linked data platform part of this as well. So it will give you some hints on how to navigate across different records and different levels in the catalog hierarchy. But I'm not going to go too deeply into that. And if you want to learn more about that part, you can go into the specification and look at the tutorial or demo. The DCAT has been extended slightly here, and some examples is this fair data point type of resource, and that one always contains the endpoint URL that I mentioned. It also has a required metadata catalog, which is the entry point to the DCAT catalog. And then it has this conforms to, which is defined to be a shackle compatible description of the schema for the metadata records themselves and not the data that they describe. So that is very helpful to a machine agent that wants to explore it. And in the EGPRD project, we have this fair in a box configuration of the fair data point. So these slides contain links to these pieces of documentation, and it describes how you could set up your own version of this and configure it with some example data. So if you want to play around before the tutorial or the hackathon, then please feel free to explore this. And then there's also a example of how you go through a configuration of the reference implementation to be more in line with the fair in a box and the EGPRD stuff. And then I also have some slides here which are just examples of how this kind of ties everything together. So in EGPRD, they have defined this metadata schema, which is basically a way of restricting the DCAT catalog space and enhancing it with some additional vocabularies that are useful for resource discovery and could support describing different types of services. So you can discover service endpoints that would be useful for the types of queries you want to do. That includes, for example, the beacon implementations that so far have been addressed, and could also then include Sparkle endpoints and other, I mean, more advanced queries in the next few months. And if we look closer at the image down here, which is basically a picture of the metadata schema in, I think, UML, this kind of gives you an idea of that there are some mandatory terms in addition to the DCAT standard, and there are some new ones that were not part of the DCAT standard at all before. And there are some examples of how these, I mean, have been specifically adapted to certain types of resources. So this is the patient registry. And there's also some templates for those who are more spreadsheet prone. So there's a similar spreadsheet with columns for the different predicates that you would give in the turtle representation. And it's the same thing for the other parts of the vocabulary as well. So, I mean, even though you want to end up with turtle and kind of this linked data approach, you can still start with the spreadsheets and define some mappings that would do the translation for you. And there's an onboarding procedure for the EGPRD on how you kind of start with preparing your metadata, designing your schemas, and then configuring your FAIR in a box installation to get this working. But you could do this on whatever system you have. If you want to do the mappings yourself, interact or decide exactly how your turtle is supposed to look like, then you can just implement the specification by yourself as well. I mean, basically, what we end up with is a turtle file like this one, which is ingested in some way in the virtual platforms registry, and then you end up with a resource that's listed and searchable in the virtual platform interface. So I think that was the last slide.
So now in a couple of minutes, we will go to the coffee break, so you can rest a bit. But first, I thought that maybe we could show you how a FAIR data point looks like before we go. So this is the interface that was created for one of the FAIR data points that we created for the hackathon for the last day. And this is a human readable interface so that humans can interact with it and read it. But what Worman has explained is that there is a layer that this is also a representation in a way that machines can understand it. So as Worman was describing, we have catalogs of different types of data. We have information about rare diseases in Andalusia for wobbly possums. And then we have the data sets themselves. And if we go into it, we can see that we have one data set in particular about the outbreaks. And these outbreaks has some services to be able to query the data. One of them is an API access that restricts the terms you can search, and then the other is more free, Sparkable. And yeah, that's everything. You can go now to the coffee break. Please be back in 20 minutes, but Marco also wants to point something out. This is a layer on top of your database. Sorry, let me move this out of the way. Okay. So your database stays as it has always been. You know how to interact with your database, so we don't want to change that. The way that we do things is we have a data transformation layer on top of your database that transforms whatever format is on to an RDF format. And then we also have the FAIR data points that serve as metadata publication. These are the components to FAIR in a box. We have this is a copy from the GitHub repo. So we have the FAIR data point, which is a metadata service. That's what I'm presenting right now. Then we have YAML, which is a template language that allows to transform for example, CSVs into RDF data. That will be my colleague Pablo here that presents that part. And then we will also go through the GraphDB section of FAIR in a box, which handles the data storage. So FAIR data points handle metadata. GraphDB is like a database for your data, okay? These slides are based on a lecture. That was created by my boss, Mark Wilkinson. So thanks, Mark, for letting me use part of your lecture for this. And before we begin, I want to give a disclaimer that there are actually 3 ways to interact with FDPs. I forgot to add one, sorry. You can interact with it programmatically using the user interface that I showed previously before the coffee break. And then there is a intermediary part where you can code, but you have interfaces for that. I will show that later. So don't be scared if you are not a technical person. There are ways for you to do this as well. Now, how many of you are familiar with REST? Can you please put your hands up if you have heard of REST before? Good, perfect. So for those of you who are not, REST stands for Representational State Transfer, and it's a way to create software that is aimed for software longevity. Most people think that REST is only for creating APIs to read information from somewhere, but REST also defines ways to write information to places. One of the most well-known and used protocol, which is the HTTP protocol, is well suited for RESTful architectures. And that's what we use to interact with data points. So I will explain now quickly the different ways you can use HTTP. First of all, in HTTP, which you are used to seeing, it's what you put when you interact with the internet. You interact with websites, right? And in HTTP, we have representations for things that are not only websites. So we also have, for example, RDF representations of resources. We have a set of universal calls in HTTP that are generic and that we will go over today, which are get, put, post, head, and delete. These are the most basic ones. There are more for more specific cases, but I will go over them today. Okay, so first we'll go over the get call. You have the method definition on the QR for each of these calls, so you can check if you want. But get, what it does is retrieves the current state of the thing. So if, for example, we say get an HTTP example.org things1, we would get the default representation on that server of things1. But we can also specify the exact representation of things1 that we want. So for example, if we say get accept image JPEG and the same address, we would get, if possible, the representation in an image form, JPEG format of things1. Then put is a way to write content to resources. And what this does is it creates new states for the thing. And if there is already a state that already exists, you can overwrite it. You can do it from scratch. So for example, if I say put some data into HTTP example.org things2, I would create things2 containing that data. And if there was previously data on things2, we would remove it completely and change it with the new data, okay? Then we have the post call, which is similar to put, but with a twist. Post only creates new things and specifically creates subordinates or childs of the one existing thing. So for example, if I say post whatever data into example.org things, it would create a new subordinate of things that could be things3. And then we have head and delete, which are the last two ones. Head serves to get relevant metadata about the thing. So for example, if I ask for the head of the container that contains the things 1, 2, and 3, I would get relevant metadata like what kind of calls can I use, get, post, delete, and everything on this particular resource, on things. And then you can also ask for the, you could also get back what kinds of representations of the things can you get from that server. So it will tell you can get JPEG, you can get HTML, you could get Turtle, whatever. And then we have delete, which is really dangerous, of course, which removes the things completely. And the thing is that if I say, okay, I want to remove example.org/things/3, I would delete not only the data, but the URL itself. So it will no longer resolve. You're probably familiar with 404 errors when you try to go to a website and it's down. That's what happens when you delete it. And then here we are going to start on the programmatic part of interacting with things. So curl is a command line tool for making web calls. And this is the anatomy of a command that uses curl. So we will say curl/L, which is follow redirects. We will see what that means in a second. Then /v means verbose, which is please tell me what you are doing. X, which means execute. Then in this part, we have get, which is the call that we want to perform. Then H is the headers, what I told you earlier, that you could say, okay, I want to get exactly text turtle, not an HTML or JPEG, only turtle, please. And then the resource that you're trying to access would be the last part. So in this example, it's not field, but it could be wherever you want. So we have a server running right now, which is an LDP server. I will explain what that means in a second as well. But if, one second. It's hard to do with one hand only, so excuse the slowness. So somewhere over here we have this server. I will try to make this bigger for you so you can read. So we have a server that contains a folder. It's not really a folder, but it seems like a folder here, right? This is what we call a container. I will explain them in a second. That is called training, okay? So if I go to a terminal, okay, we are having trouble entering the terminal. So if we execute this command, sorry, this requires 2 hands. No, zoom. Yeah, sorry about that. We are going to execute the command that I just showed, where we are going to just get whatever is in that server, okay? So if I execute this, we get a lot of text, okay? We're going to go over it in a second, but if you check here, we can see that inside of this, there is a container, and that container is called training, okay? So now let me switch back to my slides so that I can explain what all that text means. Yeah, as I said, this is what matters right now in this exact moment. So we have a container that it's called training. And now I'm going to introduce the linked data platform. And we have these beautiful Matryoshka dolls. And linked data platform consists, I'm hitting on all the wrong buttons. Okay, so it consists of containers, as we saw before with the training one, that contain other things. Some of the things that a container can contain is another container, and maybe that container contains a resource. In this example, all the text we had seen previously tells us that we have a container, and the text that is marked as yellow, that contains one thing, and that thing is another container, okay? It's as simple as like having a folder structure, but they are not folders. Then inside that training container, we have another thing, and that thing is a resource. What's the difference between containers and resources? Resources contain the data itself, okay? So, and we have some additional metadata. And let's say that I didn't want this last part to appear, the post call, but we are going to create a new container and resources. Is there anyone here that could maybe tell me already why we use post instead of put? Any ideas? Yeah, she said that way we create a child of the existing resource. and that's correct. But we are going to use post because FDPs handle things a bit differently. They don't allow you to specify exactly what the thing is going to be. So you have to post it. So you can know beforehand what the URL will look like. So you have to post. Okay. So this is the container and resource that are inside of that server. And if any of you are familiar with RDF, this might be weird to you. Why are these symbols here? In the link data platform, this means that I am a container. Okay, that's what this line means. This is a toy example, of course. The real metadata would be metadata, not only that. And then the resource itself has the same, says, this document, I am a resource. Okay. So if you want to then follow these steps, you can take this this presentation and go over the steps, and then you can create the training structure that I showed you. I will show how to do it. So to post things, what you have to do is use curl as well, use post. The different things that are new here are we are asking the server to create a subordinate. We want the server to know that we are sending on turtle format. The Slack means that I would like the new subordinate to be called training, if possible. Then we need authentication for post because we are editing what's already there. So this is simple user password credentials. And then we tell them, okay, I want to send this data, which is the container TTL that I just showed you. And it's as appears on the bottom. Again, this says, I am a container. And this is really important. When you are using post, a reminder, you are creating a subordinate of a thing, not the thing itself. So you have to carefully think about this before doing it, because otherwise you will create things in the wrong place, okay? So you have to create the training container that I just told you would be a child of the LDP container, okay? So let's go over what that whole wall of text is. So first we have, okay, we used HTTP 1.1 for this. Then the server returns a code that is 201. 201 is a happy message. All the 200 messages are that the operation was completed successfully. Then it told us that it created the training container as we told them to do. And then it explains that it has created the resource that we wanted it to create. Let me move this bar again. Sorry. So in this particular example, the server is lying to us. It's telling us that it created HTML. This is just a bug with the server software. It created a text turtle. And then if we go over again, we would see that if we perform a get on that same server, we would get a 200. Okay, we could access that. Then that server allows for get, head, post, pot, and delete, and much more calls, but we covered those ones that are highlighted. Then what kind of content that server accepts. So in this case, it accepts turtle and N3, NT, which all are RDF formats. Then it also accepts HTML, and then it also allows for LD-JSON. Then this tells us that the content type is text turtle that we got, and that it contains this container, the training container. Now I will go over the FDP API, now that we know HTML. And as Walmart presented previously, this is the basic DCAT model. And the most important parts are catalogs, which have the property of dataset that links them to datasets, and then datasets have distributions. Now, I have codes if you want. We have two different FTPs already deployed. We have this one that is filled, so you could see what a FTP looks like. That's the one that I saw before the coffee break. And then we have this one that is empty for people to interact with during the hackathon. Now, one of the ways you can interact with the FTPs is not only using the command line, but you can use the user interface itself. So if you log into the federated point, oops. I don't remember the default password and user, sorry, but I have a screenshot here. So if you are logged in, you can hit this create button. And then, no.
We are using different computers, so we have to go with the credentials from one to the other. So sorry. Which is the password?
It's okay. We can come back to this later, but it will prompt you with the option to create a new catalog. It will ask you for the metadata fields that you have to input, like title, version, identifiers. You can also add the license for your data, the language it's in, things like that. And another way to do this is to use the Swagger interface. For those of you who are not familiar with Swagger, this is what it looks like. It is an interface, a human interface that allows you to perform the exact calls that I showed previously. So for example, you could post a new biobank here, or you could get, put, or delete. So this is another way. And now we are going to interact with the FTPs using the command line. Oh, here it is. So maybe yeah, it was, sorry. Yes, we did change it. Yeah. So in the case of FTPs, the security is a bit more complicated than simply putting your password and user. So you have to contact the tokens service of the FTPs, give it your email and address, and it will return a token, which is this part here at the bottom, which you should never share like I'm doing right now. This is an example. And then all your next calls will have that token to identify that you are the person doing them. So you have access to that server. I will show it later. So we can create a new catalog using the minimal required information from a federated data point, which is all this information. And if you create a new file and then post it with this command, as I said, one of the headers now will be authorization bearer and the token. And then you pass it the data binary that we just saw, the data catalog 5000 TTL. And it will create a new catalog. It will begin in the draft state. And you have to then update this last part, the meta state, so that it becomes a real catalog. And once you have done this, we have our own FTP index and virtual platform. So the FTP index, I don't think my colleague Wermar explained this, but it's a place where all the FDPs ping to and say, hey, I'm here, I'm alive, please index me. And then they all appear here and we have information about if they are active, invalid, or something happened with them. And then the virtual platform that Walmart mentioned consumes this information to create all the querying capabilities. So this is the virtual platform. As you can see, it's quite different from the one that Walmart showed. This is just to show you that as long as you have the semantics there, you can create your own implementations of almost everything. So in this case, this is a virtual platform that we created for another project that my boss and I are in that uses germplasm resources, but it's consuming those two data points. So as you can see, we have one disk. This is the normal browser, not a screenshot. We have the FDP that contains information about the wobbly possum. Then we have its datasets, the distributions. Sorry, there are no distributions. And then the two ways to interact with it, which is the beacon API that my colleague will explain right now, and then a way to interact with it using SparkQL. Then you can also search the different catalogs by keyword or by ontology. This is similar to what Cesar showed at the start of this presentation. And then you can interact with the different data services using this section here that will allow you to select to which parts to which catalogs, to which resources you send your queries and get information back from. And yeah, that's everything from my part. Now it will be Pablo's part. So thank you.
Any question for now? No? Okay. So let's wrap up a little bit for now. We have explained how to interact with metadata with the virtual platform and the resources that is inside. And now I'm going to move to patient data representation. So there's two different, we have two different approaches, one for the metadata that describe the catalog, the resources that there's inside. And now we are going to move to how we populate real data or synthetic data, any data from patient entries. So that's what I'm going to do with KRSM, Clinical and Registry Entries, Semantic Model. The motivation for the creation of the semantic model came around 5 years ago with the creation of these, the European Joint Project of Rare Diseases and the need of a virtual platform that gathers the information, which was increasing amount of registries in the community that were interested on using semantics and the lack of interoperability between them. We are working with rare diseases that are very heterogeneous, and the need of creating bridges between different representations came. So in order to do so, we use the capabilities that Semantic Web gave us to perform data interoperability between different models, and the need of creating a federated exploration and analysis data model that gathers all the enhance that FAIR principles and semantic web technologies have. The creation of this semantic model came in two many stages. The first of all was the creation of a previous model that was the common data element semantic model that probably some of you have already heard about it. For those that are a little bit lost between what's common data elements and what KRSM is just a natural evolve. So the people behind are just the same. We have been doing data modeling for years. So we started from a very set of common data elements defined for this project, but we saw the need to expand, not just for those 13 add important data elements, but also moving into treatments, to medication, to any other representation of questionnaires, prompts. So we decided to create something more robust, more reusable, and that's what KRSM is, just the nature evolve of CD or Common Data Element Semantic Model. This is how the model looks like now. Not sure if you can see it properly, but I can later move to the GitHub page if in case that is not very clear. But the idea is to start from the patient identifier information that relates the identifier and the individual, which is in the case in the patient, that shares a common role. This role participates in a process that has an output that refers to a personal attribute from this patient, and also an input, agents, elements that can be participating on this process, target in case of any anatomical structure that wants to be represented around the clinical process of diagnosis, treatment. And also, this is one of the last acquisitions, the presence of a protocol where we define the information that correspond to any experimental protocol around this process, like, for example, prescription, a drug administration can be specified by a prescription, and several other attributes are present, like the substance, the concentration, which followed by the units, the frequency, and other protocols that could share the intensity, low, higher, route of administration, activities, like specific activities that can be part of the data element representation. Like, for example, in case of a prompt, a representation of a questionnaire, the activity could be, for example, the specific question that have been done under a common process, which is the questionnaire assessment of this entry. So as you can see here, this representation of several entities. Not all of them are always present, obviously. For the assessment of the sex of the patient, you don't need to know about the target. If you want to prescribe some drug or treatment, you don't need to know which are the personal attributes associated with this process. So the idea is to selecting which are the not selecting because are already defined, but know that we are playing with a preset of instances that are going to be participating in the model. None of them are always present, but the structure follows all this structure that allow us to have a common structure for later. So to do so, we have reused some of the schemas of the community. Rather than creating something new, we prefer to reuse something which are great, rather than creating a new standard. So all the semantic elements that shares in KRSM contains schemas that are followed by the community for years. So in order to create the upper class that defines the relationships and the instances and classes, we use semantic size ontology, which allow us to define that kind of information, like the upper concept of attribute, process, entity, identifier. And also, on top of that, in order to refer to the domain-specific information, we decided to use OBO Foundry ontology terms that follows all the ontologies gathered under the same OBO Foundry project. So with the combination of upper classes ontologies and the combination of domain-specific ontologies followed by OBO, we are capable to represent any information that we want to describe for patient data. So this is an example of one of the representations. As you see, not all of the instances, which are those diamonds, are present for birthday assessment, but all of those are part of the KRSM data model representation. So we have the assessment of the identifier, followed by a role which describes a process, of assessment, which is the birthday of the patient, and it has an output, which is the value of the formatted date of the patient. As you can see here, this is RDF, the representation that we have been talking a few minutes ago. Subject, predicate, object, subject, predicate, object, and so on. So from the output, we refers to a personal attribute, which is the birth date of the patient, defined by a NSID code, part of the OBO project. So as you can see, followed by this one, and yes, we have changed from a slide. Here we have diagnosis. The good thing is that diagnosis shares the same structure. The same assessment of the patient informations are participating in a different process, which is in that case the diagnosis process. It have an output and refers to a condition which is defined as disease or disorder with a RDF type that describe this ordo code that will be used for defining diagnosis information, or also our undiagnosed information. So different representation can be done for laboratory measurements, where there's a process of laboratory procedure that have an input, which is the sample, the target, which is an anatomical, well, the molecule that points, that targets this measurement, which will be creatinine, for example, and the output, which is the laboratory value, followed by its unit with unit ontology, which is in this case milligrams. The last, so all of those representations shares a common structure, which was RDF, but it's not just based on triplets. We also use quads, and why to do so? Well, the thing is that by using quads, we can create a fourth element that shares all the triplets that are inside of this data element. Which are the benefits? Well, we can create a context around this representation. We can say that all this information have one identifier, and this identifier is related to temporal information, which is based on start date, end date. We can use ages also. It exists at certain age where the patient was observed. And this idea of this common context gave us the possibility of creating a timeline of events. This is not just individual data elements represented. It's also the possibility to create it encounter-based information, hospital encounters, any kind of visit or context around a certain moment on time. This information can be created by referring several data elements, like, for example, the assessment of a certain symptom or two different symptoms under the same event, which will be, in that case, the clinical encounter. This is one of the highest changes from CDE to CARE, the possibility of creating this context around information. So it's not just individual entries. You can also, if you want, create this encounter base that will allow us to be interoperable with other standards from the community that use this encounter structure, like, for example, OMAP. Yeah, so as I said, interoperability with healthcare data centers. This was made due to the fact that that there's a consistency structure through all the data elements. So all the data elements share the same structure. So first of all, we can create a smarter ways to template this information into RDF, into semantics. So not the information which is basic from the patient, like sex, birthday, diagnosis, are computed in one way, and then the rest of the information computed in another way in a different data table. No, we treat the same information the same way in order to implement it. So smarter, more efficient agents can be created to populate these data elements. Also, for querying, if we are treating the same structure, we can query by the same structure, which is, I believe, the most interesting thing behind the model. It's hard to create Sparkle queries for anyone, for people that works on 1 year to 10 years in the community of semantics. Creating a semantic, a Sparkle based on this structure is hard. So in order to enhance the people to come to GRSM, we have created this common structure that can be queried for anyone. You want to specify a certain triplet where it's going to be treated as diagnostic, you can just filter automatically by using the same Sparkle query. So smarter agents can be created for querying, exploration, and transformation. Also, in order to be interoperable with the community and all the resources that shares this virtual platform, we have created a Beacon API for KRSM. The interface of Beacon defines by the specification several filters of the information that you want to retrieve for data discoverability and exploration. This information is based on JSON, and we have a structure on RDF. So we need to convert somehow this information, which is made on JSON, to a Sparkle. So due to the necessity of the virtual platform and all the resources that participate of querying anonymized patient counts, we have created this Beacon API where you can define filters. Here, I will explore the filters later, but this will be one of the filters. This is the anxiety code for symptom of onset, defined as a 7 with an operator or more than. The same for sex information, if it's female, male, undetermined, and also the HPO for phenotype or symptom information. So here we have several filters, and this interface is going to transform this structure based on Sparkle. If we were not using the same Sparkle query for obtaining any data element representation, so if we didn't have the same command structure, that would be so hard that probably will, in order to deploy this system, we will have to go query by query and finding common grounds. But due to that, we can treat these Sparkle queries as modular, and we are capable to define filters based on a common structure. We are capable to make this transformation to a Sparkle. So it sends this Sparkle query. All the credentials are treated in this first step based on the Beacon credential specification. And once everything is accepted, we can convert, sorry, I put convert, we can convert to Sparkle. It's sent by HTTP post, the Sparkle query, and it retrieves an anonymized count of patients that shares these filters. So no information is exposed. This is the real response from the server. We can explore the patient information, the sensible one, can be filtered by this procedure. So this is one of the benefits of using this kind of counting system. So are totally anonymized, and we can keep the patient data secure inside of the repository where the RDF representation is. I wish also to mention that in the EAP, we are also working on other interoperabilities. In that case, with OMOP, we are creating some kind of ETL, extract, transform, load workflow that takes the data represented on our KRSM, and via Sparkle is structured, is transformed into the compatible representation of OMOP, and then is loaded or injected in a Postgres database for those kind of services. That's something that we are working on, and hopefully in just 1 or 2 months, it will be consolidated by a paper. Well, the demonstration. I'm going to do a demonstration right now, but I wish also to take into account that I have 3 different presentations related with KRSM. So apart from this one, I will be presenting the paper that consolidates KRSM on Wednesday. morning. And also the midday during lunch, I have a demonstration. So you can join us and know more about the theoretical part of KRSM, and also any demonstration that you are interested to know more related with querying. So please join us, grab your lunch, and let's talk about KRSM if you are more interested on several details. So how can we populate KRSM model? What I said just before is just a theoretical representation. So you can implement KRSM as you want. To make things easier to the virtual platform resources that we are working with, we have created different one way to make it easier, which is based on YAML and CSV templates. YAML is deployed by Farinabox, which is the interface that my colleagues were talking about before. But just for you to know that if you use the interfaces provided by the virtual platform, all of those are compatible with KRSM. Implements its own templating thing. So the only thing that you have to worry about is a CSV template. One of the things that I said, which is important of using a unified model, you can have a unified CSV template. So you don't have to worry about creating different representations. It go everything under the same data table. So you just have to populate one single data table, and all the columns are here. So it requires no change of it. We have in the GitHub Docker, in the GitHub documentation, an example of this empty template. But just for you to know that there's a static number of columns, which are those that describe the patient identifier, the values, some classes that can be part of the representation, protocol frequency information, and temporal information mainly. So each one of the data elements will require some of those columns, not all of them. So how can we transmit which are the columns required? Well, we have a GitHub documentation for each one of the data elements that we have detected and defined. So this will be how to populate diagnostic information. We have a legend that says all the information that it's required. In case of any, so if you have this information, it's good. It's optional and it enhances the representation of it, but it's not required for creating this entry of data, and those are not needed for this representation. So in case of diagnosis, we define a tag which says that diagnosis, the patient identifier, the value, which is the ORFA code, could be the one that says my colleague Cesar, the orphanet 666, and also temporal information, age in case of needed. You can put any human readable layer you want to complete your information with more information, and an event ID in case that you want to relate this information with any visit encounter of your registries. Not required, but in case that you want it, you can do it. That's another example of medication data. So as you can see, the difference of the data of defining a diagnosis and medication is very, very different, but you can do it by populating the same template. So it makes everything easier. So you just have to, if you have your SQL, your database on a database, you can point all your SQLs to be pointing to one single data table. You don't have to worry about creating different data tables. You can put everything inside of the same standard, which I believe is useful for the users and make everything easier. So medication, rather than populating the value of the condition, well, we have to put different information like the agent, which is the drug, the route of administration, the frequency. the units of this concentration, some of them are common, like for example, PID, the personal identifier, a different tag, and you can continue using the same temporal information as that. We have a Docker, a GitHub page that informs each one of the data element representation and gives a glossary for each one of those. I will jump just in a few minutes to this representation. Yeah. So the idea is that taking this YAML template, which is the same one for any data element because it defines the same shape, and the curated CSV can be done by a toolkit that it's implemented on Fair-in-a-Box. We are capable to transform your CSV template into a semantic representation of your data defined in RTF. I have prepared an example of mock data or synthetic data that I have created just to explore a little bit how will be the queryable part of this implementation. It was just 120 registries patients that have several data elements, like for example personal information, birthday, birth year, sex, symptoms, several different symptoms, hematuria, vasculitis, cystinuria, and more than 10 different rare disease diagnoses, like for example, homocystinuria. All of those diagnoses are defined by orphanet codes, the same kind of codes that my colleague showed us a few hours ago. And the genetic information, one of the assessment of a certain gene variants. So I'm going to jump to GitHub. So I want to show you where this information is located. First of all, we have a GitHub repository prepared for that describe the CARSM model, several information in order to understand the context of this model, the representation that I show you, and this is the list of different data elements that we have identified. Personal information based on demographic data, from birthday to body measurements like height, weight, body mass index, questionnaires or prompt representation like what type of disability you could have, education level, symptom onset when you started feeling this kind of sign. You can define also which sign are you referring to, participation status and its relationship with the medical history, person counter visit, conditions of any kind, phenotypic symptoms or diagnosis, and several measurements and treatments also. Genetic information, we are expanding this representation, but the idea is to align with the necessities of the community, working on more a more heterogeneous genetic representation. So not just zygosity, amino acid locations for proteins or gene variants, but we wish to continue working on that part, and some information related with viability and consent and clinical trials. So we have defined glossary for that. Let me move a little bit to the other repository. Sorry, just a few seconds. Yeah, here. So in order to populate the CSV, we have also a link that describes what do you need to do so. So here we have all the required columns. You can directly copy this example of an empty template, which is totally basic, just the column names. So you can start populating by your hand or directly use it from your SQL database and start populating this kind of information. So the same data elements. So for example, let's go to the the diagnosis representation, as I said. Here it is. All of them are concatenated one to the other. So you can see that all the definitions are described for any type of representation of the data entries. If you consider that one of the data entries that you want to be populated are not part of this representation, please let us know, and the community that are working around KRSN will make it to expand this representation to be more aligned with all your necessities. As I said, I have created a mockup data. So this is the result of the creation of that table with mock data. So here we have the model defined, the person identifier, and at the end you just need to create something like this that defines several codes for your values, or if the value is in a certain excess D, like a string float, you can define it in values. So this is how a resulting data table will look like to be compatible with KRSN. I'm not going to jump into the execution of the data. Everything is described in the Farina-Box solution in case that you wanted to use it with this interface. We also have document a standalone representation where we have Dockerized all the information that you need to know in the same KRSN implementation repo. If you go to standalone implementation, we describe what kind of requirements do you have. Everything is Dockerized, so for the community it makes everything easier. But if you want to skip this part and go directly into the data implementation, if you already have Farina-Box, it's easier because every element, every artifact, like for example YAML, are all of them updated and maintained there. So let's go to the querying part. So we have so as I said, you can use the same structure for retrieving every data element that you have. So by one single query, you can extract all this information. This is the example of the query that defines all the elements that could be part of the data elements. If the representation is updated to represent more elements, the query is going to be the same because it defines all the pre-existing elements and queried. So yeah, I'm going to execute this query so you see how it will look like the resulting information. So as you can see, by retrieving this query, you obtain all the elements that you have already seen stored in the CSV. But now from the triple store where we define the RDF data, you can obtain mostly the same structure. So you can always go from RDF to non-RDF representation, but for you to know that by using this representation, you have the semanticized capability to move in to a data table again, or extract any certain element from here. So for example, if you just want to define that rather than having birth year, sex information, symptoms, I just wanted to obtain information that is defined as a diagnostic procedure, that will be the definition of symptoms or onsets. So you just have to make small adjustments with just one single change, will be including this entity class that defines a diagnostic procedure. Just by adding this single thing into your Sparkle query, you can directly obtain only the information related with HPO codes that define signs or symptoms, or phenotype information, and orphanet codes that are inside of the data. So for those that are not used to working on Sparkle, just to know that if you start from this Sparkle query, you can, by small changes, obtain your specific data. I was sorry, I want also to show you how this beacon implementation will look like. You already saw when Cesar was show us how to filter by age, symptom onset, and how the interfaces was capable too. Behind of this representation was a request of beacon by specifying several filters. We are going to now see how those filters look like from the code. So I have opened here the beacon API where it's running the implementation that is going to take just the JSON request and retrieve a certain number that will be the result of it. It's just the same, but from the backend. So if for those that are interested on middleware communication, API assessment, just for you to know that this KRSM is capable to perform those kind of anonymized filters behind using this API. So yeah, it's connected to the triplet that is running here. And let's first inspect what kind of filters are available, because probably you have only diagnostic and symptom information, but you don't have genetic information. So rather than giving you 0 because it not passed the filter, let's see what kind of filters are available. So here you have, okay, now I know filter sex, diagnosis, symptom, gene variants, birth year, age of symptom onset, and age of diagnosis are available. So now I can know that I will do those filters and it's going to serve the information that triggers, it will be present in my database. This information can be easily deployed when you implement this beacon API. Everything is documented and it's very easy, just defining some environment variables. Yeah, let's go to the post. Let's see how it look like. I'm going to copy one of the exemplar beacon requests that will be this one that says, okay, this is a an API version of beacon 2, version 2.0, and the type that it's pointing to resays disease or diagnosis. And I want to know which are how many patients shares both this orphanet code and that orphanet code at the same time. So 2 different diseases. So let's copy this information. You don't have to do it by your code, but just to know that everything behind works that way. So here we have, let's need a third hand. Okay, thank you. By executing the information, it retrieves that just one patient shares both these diagnoses. Let's go to a different examples that where we can play a little bit with this kind of information. So, sorry. The case of searching for a symptom, certain onset, the age of this onset, and the sex of the patient, which is in that case female. So let's copy that and try to do it with a different, yeah. So it says 11. Okay, let's increase it a little bit. Let's say, okay, I just wanted to know how many shares more than 8 years of onset. So the number decreased because the filter defines more restrictions on that. So you can play a little bit with that if you're interested on engineering semantics, or you can directly use it, the one that my colleague shows in the very first moment of the presentation. All this information related with beacon, which are the permitted filters are defined in our in GitHub also, and all the information will be located in our presentation. So if you want to check for more documentation, here you have the link that shows the beacon code if you want to inspect it and see how it works from the code. You can also know which are the available filters that can be used to use beacon, and also the exemplar request body that I have shown you, the 6 that I have created for this tutorial. You can inspect it on the GitHub. Also, you have also the link, so be happy to check it and call me in case that you have any question around. I'm going to continue talking about KRSN on Wednesday, and I will be here all of those days. So you have any question, raise me, or you want to inspect more in deeply some of the things that I have been using for this tutorial. So thank you so much.
Yeah. Any questions? Okay. I expected so because this has been dense. Oh, Walmart has a question.
I'm going to give you the microphone. We have another one.
All right. So do you have any reflections on how to implement these or use the KRSM models for more advanced queries going forward? Let's say federated queries and more kind of in-depth things.
Work? Yeah, perfect. I think that relates more into the implementation that are used in KRSM. So KRSM is just a data model. So it goes on top of the interfaces that can be used. So for federated analysis, the virtual platform are working on this exploration via federated, and we know that Fair-in-a-Box, the interface that use KRSM and it's compliant with, it's performing federated analysis through all the BP resources. So that's the kind of two-chain registry that have tested the possibility of using this semantic model and all the implementation of the virtual platform to perform federated analysis into different resources using this Sparkle system that sends the query to every resources connected to the BP index. We are working on that, but yeah, we are thinking as a KRSM as a solution for this federated analysis and exploration. Yeah. Any other question?
Marco, okay. But just before Marco's question, since this is a very dense tutorial, I also wrote down some questions that I wanted the audience to think about, and maybe we can discuss them after Marco's question. So, okay, yeah. So one of my questions is, let's imagine that you are, or in reality, you are a data owner. You have some data. What's some of the metadata that you think could go into one of those FDPs, fair data points, to make people interested in collaborating with you? What kind of information might you find useful in possible collaborators? So not only if you have the data, but let's say that you want to find a specific data for your use case. What would you look like what could you look for in the metadata? So one example of metadata, oh, sorry.
Yeah, presence of some specific variants. I don't know if this is allowed in rare diseases cases, but I'm thinking if I want to interoperate with other data sets, maybe I'm looking for other people that are looking for variants in specific locations, or I don't know, something like this.
That's one example. I think Walmart had an idea.
For that question, this semantic model is not just meant for rare diseases. It's meant for any clinical representation of data entries. So we have used the example of rare diseases because of the need of using these kind of technologies in a very heterogeneous data representation. But that can be used for any gene representation encounter, like hospital information and also rare diseases. But rare diseases is was what the original purpose, but we are working on using this KRSM not just for that, but also for genetic representation tools. Yeah. One more?
Yeah, so I mean, expanding a little bit on that question as well, I think I would be curious to see if people think that they either have a use case that they think could be compelling for the federated approach. I mean, where you might want to do queries on a virtual cohort of some sort. I mean, filtering patient information and variant information in combination, being able to run and aggregate across several kind of resources. And then on the other end, so what kind of synthetic data or existing data is available that could be then, I mean, could be used to shape a model or improve the existing model for the rare disease case to address that example query. So I would like to see some more kind of, I mean, those kinds of queries, but on some synthetic data that could showcase it without necessarily having to touch people's real data and getting into the legal discussions.
Yeah, I believe that the feedback of the registries that are working on or interest on KRSM will enhance quite a lot the implementation of this kind of data, because the implementation of the model and the creation of it, we don't have quite a lot of data representation example, and the more we have them, the more refined, stable, and robust can we be with this kind of semantic representation. So yeah, I'm also interested on this kind of representation for the data modeling part by refining it with more and varied data for that. Yeah, sorry.
Yeah, so I'm Alban from France, and we are working on a national project on intracranial aneurysm, which is not a rare disease, more common disease. And we have several, let's say we organize data based on the modality of data. And we have medical imaging data, which is in a medical imaging database. The same for, we are a bit less organized for genetic data, and we have clinical data sets. And we would like naturally to issue some federated queries to combine clinical observation with genetic variants and with biomedical imaging markers. So there are plenty of scenarios for doing this kind of queries.
Yeah, our first exploration of CDE and the resulting KRSM model was tested by using some representation of medical imaging apart among them. But yeah, it will be incredible to have this kind of sample that comes from a registry that represent this medical information to enhance this kind of model and see all the possibilities that could be raised by doing this representation.
And I have another question. So this morning I was attending the FIRE tutorial. So is there any alignment with the FIRE data or FIRE RDF data model?
Not between KRSM yet. I think it was proposed from the beginning of the project. But as far as I know, there's not direct transformation from one to the other right now. If FIRE is represented in RDF by this FIRE to RDF representation, those two data models can be, let's say, easily transformed by by one schema to the other by using a Sparkle construct, takes the information of one place and put it in the other. So the connection is not yet done, but hopefully we can be interoperable not just with this specification on OMOP, but in future with also FHIR representation. Yes, Marco?
Yeah, maybe this good to mention that some mappings have been tried, or have been, others have done some work on. So one is OMOP, and I think maybe even through OMOP, some connections to FHIR have been done. There's also been a use of the same pattern that we're using here, but then using the OBO Foundry ontologies. And it's indeed based on the idea that the core model to define any data element, that is a pattern, that is a semantic pattern that you can use and translate into other ontological frameworks. And indeed, we hope including FHIR. So, yeah.
Thank you, Marco, for that.
Can I continue with mentioning one thing? So we have on the biohackathon list, we have I think 2 ideas for the biohackathon that are related to this, and one is also with the idea, basically the same question that we're discussing now, to see if there are some ideas, because we love to get ideas from all of you on how would you use basically any part of this, or extend it, or use in a slightly different way. The core is the semantic models, which makes it pretty flexible in going towards other areas, and we would like to know. And maybe at the biohackathon, maybe a few we can actually try if there are some things we can try. So FHIR could be one, right? That we could try. Oh, can we actually do a few steps towards FHIR and see how that works? But also, sort of now we did a connection to the Beacon API. Maybe there's other APIs that people are working on and would like to see. Oh, maybe I can do the same trick, but then with a different API, etc. Technical, non-technical. That's and the question I had for you is the question that you asked before the break with the Mentimeter. Would it be? I'm maybe asking something impossible now, but would it be possible to open that up again? Because that's basically the same question that you asked, but then people can share that via Mentimeter. But please continue brainstorming. I'll bring the microphone to the next person. So can I ask something of the audience then, while I'm standing?
Yeah, go ahead.
So who would consider themselves presenting a provider who would be using this to expose data to others? So you would be one, and you would be one. And who would consider themselves a technology person, who would be an enabler? So that's other people, right? But Philip, can I bring it? Because maybe you have some ideas of how you would use that for your, maybe you can say something about your data.
It would be an idea to apply it, but what we are currently doing is trying to manage person-centric data vaults. And if people are willing to share information, we could create a kind of an aggregator to make things available, anonymized, for example. So that would be the idea, so that you have direct relationship between the data which is generated and managed by individuals in their personal data pots, data vaults, then an aggregator service, if consent is given, can aggregate information and can make it available.
So that would then be an application, a personalized application, but in principle, you could imagine using the same models.
Yeah.
And in fact, we need to talk because we're actually in contact with Belgian peoples about personal locus, etc. But yes, or just a copy of the same question, but then asked again, now that they've seen all this. So the reason that you're at the Semantic Web conference, so the idea is that Semantic Web is extendable, in all sorts of ways. So then you can have ideas of, I would extend it in this way, or I would use it in this way. And we're all curious about that.
We can repeat this one, you mean? Yeah. Oh, okay. And as a reminder, you can join it by going to menti.com and using the code on the screen.
Don't worry, raise something, repeat it.
Yeah.
If you don't mind sharing.
And I guess that for this question, you should also consider instead of what would the VP would allow you to do, what it should allow you to do. Yeah, are there people online?
Yeah, even if they don't appear on the Zoom call, there are people online. So
Okay,
you
yeah.
can also participate online participant. Your participants after all.
So some people said to use it as a research machine for rare diseases, to find potential genomic data sets based on particular phenotypes. It would allow a semantic empowered search over disease terminologies and available data sets, federated exploration frameworks, set up small cohorts of patients to perform studies or trials, identify relevant resources and data sets to apply for access, to shopping cart batch application. I like this. Be able to make aggregated data available derived from person-centric health data vaults, and define a virtual cohort to run federated queries on and get as little data as possible, but as much as necessary. Good one. To find interesting test data sets for new algorithms development. This is also nice from the developer's perspective. Do you want to comment on?
No, we're just discussing technicalities. So maybe if you go out of presentation mode, then make it bigger and then go back to presentation mode. Maybe it gets bigger then, because it is a browser application. It was just what we were thinking.
It doesn't work. See, Zoom is already like on 300%, and it doesn't increase.
Okay. Well, we tried.
Yeah, Mentimeter is not collaborating today. So
I had another question to the audience. Who would consider themselves a data scientist? I saw one question about I would like to do research on it. Who would consider themselves a data scientist? Doing the analysis. We have 3 people, and Alex as well. Yeah. So do you have ideas of how you would use it as a data scientist? What things you would like to, what type of analysis you would like to be able to do? You have ideas for that? I can count.
May I first ask a question about how to query the system? Because if I have a research question, will I be able to explore, to browse, or do I have to first formulate my research question and then, let's say, ask for access or something like that, and then do my analysis?
So I can first try. Maybe Luis would like to continue. I see Luis looking eagerly. I think there's many facets to this. This is a very good question. There are many facets to it. So one of the things that I was also eager to show here at this conference is that we are creating this semantic layer in our rare disease virtual platform. So you can imagine anything you'd like to do with linked data, with the semantic data, you can think about, because in principle there is this semantic layer. We're also advocating to everyone do this, because then we can tell people this semantic layer exists. The second thing is, do you have permission to use the data under that? So you know the data will be interoperable under the hood, but in some cases you may have permission, in other cases you won't. I think Wolmar already alluded to that before the break. And that's a sort of an issue on its own that we're also working on federated AI and also capturing in a machine actionable way your access conditions. But in a way, it's a separate thing, and so that can be either through nice, super advanced automated ways, or the old-fashioned way that you get consortium agreements between people that say yes, now you can, and then you can run these queries. It's also interesting, actually, from the same group of Pablo and Alberto, Mark Wilkinson, who will be here tomorrow, has worked on a governance model where the data providers agree on which queries are allowed. So they're not saying which data you have access to, but they're saying which queries they allow to be run on their data. And because you do this in a semantic way, the queries are very transparent. So you really know what you're agreeing to. Whereas others might want to do the classical way with data agreements. What we hoped also for this conference was to make sure that we make clear that there is this semantic layer. So in principle, you can think of all sorts of questions that you want to do, all sorts of analyses that you would like to do, because that also, again, would be for us a way to see, together with Luis, we're working out this federated analysis to also push towards the community saying, yeah, please do these kind of things, because then we're making it a whole lot easier for data scientists to have their data algorithms run, not even run them themselves, but to have them run on location. Sorry, Alberto.
Yeah, it's okay. One of the things I wanted to point out about what Marco said is that they created a consortium that oversees the queries, but I wanted to let you know that it's not only the geeky technical people that create those queries. Those queries are then reviewed by ethical experts, the patient advocates, fair experts to know that they are well constructed, and also other experts that check if they are answering the question that they are asking, right? So this is not only for the people that build the SparkQL itself, but for other experts in the field to analyze, to use.
And just to give one example, it's the one that you developed in your group, is the time to diagnosis, which technically, I guess, is a pretty straightforward query on this model that Pablo showed. But for rare diseases, it's one of the main issues that we're dealing with. And in principle, we can now show that we can answer that query in a federated way.
Yeah.
Instead of having to aggregate all data around the world into one place, which will take several lifetimes and probably forever.
So one interesting thing about that, what Marco just said, is that this came up because of the pandemic, right? We wanted to know, one of the use cases for this type of queries is to know how the pandemic impacted the average time it takes for a patient since they get to the hospital to get diagnosed with what problem they have, right? So this is really useful, and it's straightforward, but it's also complex in the way that this query doesn't extract all the information from your site, puts it where we can access it. It performs calculations inside of your firewall, without any privacy compromise, and then returns the results. So really interesting. So Marco, do you have any more? Because I wanted to also ask one question.
Go ahead.
I think we have half an hour. So also, there are multiple ways to query the information. So we have queries themselves. Then Pablo showed how to create APIs that only interact with what we call faucets. So for example, only ask for the sex, only ask for the age, or a combination of both. What advantages do you think each of those types of querying has? So for example, complete queries versus only the API that takes aspects of the data, ask for sex, age, predefined things. What do you think are the advantages of each of those? Repeat it.
I just try to clarify the question, like if you mean
comparing APIs to full queries.
Yeah, because you might be wondering, if you have full queries, why are you building APIs that only take that are less powerful than the queries? Why are you doing that? Is that something that crossed your mind? No, don't move. Don't worry.
Yes, from a data provider point of view, at least you may have more control when you deal with the API ecosystem itself, because you can have more, let's say, definition of which type of filters we can use, and automated way to access your data set. And maybe people are less confident with full Sparkle type of queries in their system, and maybe also a performance issue as well. From a technical point of view, I mean, that's also something. If you try to launch lots of different federated queries across different type of resources, you may have answer or not, and the timing of that could be also a real burden. So,
yeah, exactly. He said it perfectly. Also, so for example, resources might be uncomfortable having people be able to query their data as they want, and that would means that to perform those full queries, you have to go through governance processes. So, for example, as Marco said, having pre-approved queries, or for having authentication and authorization on your data. So, for example, only people that are from my research institute and people that I want to give access to can query my data. And yeah, performance as well. Pretty good answer. It looks like he knows what he's saying.
I've one other reason that I can think of in what I observe is something as human as familiarity. So the common APIs, many common are familiar to a lot of programmers. So then you want to provide that feature because it will just attract, make it easier for those people.
And also, it's generally easier to use an API than to write a Sparkle query.
So something building on top of that, I mean, you can have predefined queries, but you can also use, you define what you want by describing the query and the expected result of that query, so to speak. So, I mean, that's how some institutes work. They basically, you need to describe what you want. They will inspect your pipeline, and then they will give you access to the data, but you will not be able to take the stuff with you. They will give it to you based on what you were expecting to bring back.
Yeah, really interesting. Yeah. I had another question. Let me check my notes because I forgot. Oh, yeah. I wanted to dive into some limitations that you might find when implementing these technologies. Do you think that every domain of science has the same amount of ontologies built for it? So, for example, in the EGPRD, we are working with rare diseases. Do you think that, for example, plant physiology has the same amount of ontologies as human information?
Yeah, I definitely think there is more in the plant physiology area, more ontologies than healthcare.
Well, actually, it's the opposite. I'm not asking what requires more ontologies, but what has more ontologies built into it, because
you mean that the current development of ontologies, current existing ontologies, that I can agree on. There's
exactly.
not enough being developed.
Because one of the limitations of any approach is the amount of budget that is given to those approaches, right? So, for example, Cancer Institute, Research Institute, gets a lot more funding than a germplasm bank, for example. So a lot more resources are put into some domains than others. So finding out which domains are underrepresented also helps a lot with improving the community as a whole.
I'm thinking of a funny thing. If anyone wants to do research on this, because there can also be overrepresentation. So maybe there's underrepresentation in some areas that can also be an opportunity, because I tend to think in our domain, biomedical domain, there's actually too many ontologies. It confuses the hell out of everyone. We have so much redundancy. So it would be nice if we could have some way to measure this.
Yeah, indeed. If I can add to this, I was going to ask if your question aimed to understand how many ontologies or how much of the domain is covered by ontological terms, or, so yeah, indeed, the number of ontology, when it's too high, it's a problem by itself. So, but do you have any suggestions on understanding what areas are currently lacking semantic web representation?
I think that the main way to find out this is to contact the researchers, right? The kind of technologies that are present in research papers. Because the way that I found out about this is for EGP, for human, but then I worked for Germplas and banks, and the landscape of supplementary tools to help with the verification. So I think that big, and one looked into more in the future. Sorry that I can't give an exact way to find out which are more represented than others, but for example, the portals that contain those ontologies, they have tags. So for example, it says this ontology is about life sciences. This is about law, something like that. So maybe looking into those things, the amount of domains that are present in the ontology portals could help.
In the meanwhile, I just have like a provoking question, because in the beginning of my PhD, we did a literature review on the use of ontologies, and we identified that the bioinformatics field is indeed overrepresented, while some other fields, like for example, I come from software engineering, Luisa as well. For any idea we have to develop a new ontology, because software engineering is not as well represented, covered, I would say, as bioinformatics. But does that mean that these ontologies, or the data, ontologized data of the bioinformatics field, is of good quality?
Yeah, that's a great question, because as we all know, quantity doesn't mean quality. And Walmart has a comment on this. I will give it.
Yeah, so also maybe a little bit provocative. I mean, depending on what you consider ontology, I mean, you could think about ontology as a representation format with the big O, or it could be, I mean, a way of conceptualizing a domain. I mean, software engineers build in these conceptual models and the kind of parameters of a problem into the software. So, I mean, in a sense, you are creating a definition of the problem domain as part of the software development process. And I mean, bioinformatics is somewhere in between the scientific domain and the computer domain. So it's maybe natural to try to translate those models into these kind of ontology representations. So I think, I mean, there's probably a lot of I mean, conceptualizations of all domains. It's maybe just that people don't choose to publish them as ontologies in these kind of well-established repositories. So they're hidden in a sense.
That was completely on point, because, for example, FAO, the Food and Agriculture Organization, I think it's an important organization that covers information about plant conservation. they have a set of what is called passport data, which is something that you can think of as equivalent to our common data elements. They are things that a lot of or most germplasm banks should contain those fields. So, for example, the species name, where it was collected, the collectors, the soil type, things like that. They have it really well written and explained on a PDF file. PDF files are hard to interact with, and machines definitely don't understand them. So what we had to do is build an ontology that represented the exact same information that was on that PDF so that we could use it. So this is a problem of publishing what you already modeled, and the importance of also governmental or international organizations to use the ontologies, because that helps research as a whole.
So a counter comment as well. I mean, so these PDF ones, when you read them, I mean, they are open to interpretation oftentimes. And I mean, and there are a lot of maybe not so great ontologies in machine readable formats as well. So, I mean, you can have contradictions and I mean, things that are just incomplete or not connected at all. Or in the relevant manner. So I think what is good enough ontology, I mean, for a certain kind of problem that you're trying to address, you probably need to dig down deeper and try to develop the relationships between some of the terms and detangle some concepts when it's necessary. Otherwise, yes, you would try to just analyze and abstract the everything.
Yeah, absolutely. The thing is that you could put the information of an ontology in a PDF file, but that is limited usefulness in that, right? And building a correct ontology takes time and effort, but it's worth. And I guess that the requirement for ontology to be good is that it's good enough for its users, right? There are standards and defined ways to create ontologies and what they should have, but if they don't fit the needs of the users, then what's the use of them? That's why most ontology developers are really open to suggestions from the public.
I would second that. There's maybe also something to mention about culture in a field. And unfortunately, the culture in the biomedical field is creating a lot of redundancy, and there's hypes, and then everybody starts doing it, and everybody thinks that they have a specific, very unique purpose. So that leads to everybody creating their own new ontology, and they indeed have the funding to do it. But it is what it is. So I think also it would be naive to think that in the biomedical domain you would ever have one ontology or one model, or there will always be a couple of them around, and you will have to do mappings, and it's just a little bit messy. But at least there is something that's then on the good side. I remember I have been in a project with Galaxy researchers, and we were the life scientists in that project. And Galaxy researchers told us that the way when they start a project, a collaboration, they first define the models, they first define the standards that they're going to use, and then they start doing the experiments. This is not in biology. You start doing the experiments, then you create a lot of data, and then then you find out, oh, nothing is compatible. So, and then you start creating models, and so it's a lot more messy. But yeah, things do emerge and do improve, but that's also a bit of a fact of life. So it's difficult to change that completely. Here's a representative of someone who has managed to sort of have the standard for rare disease ontologies.
we had to actually. That's the point. Now, my point is to say that there is a lot of legacy also, especially in the health field. I mean, between clinical terminologies and ontologies. I mean, so for instance, I mean, you have the ICD whatever version or the 11 version. You have the SNOMED. You have so that's always something which is a standard somewhere in some country. So when we try to leverage at the international level, then you enter these type of issues, and there are different purposes and different also backgrounds. So that's why it's so hard to build something. And when you come to the field of rare disease, it appears that, for instance, in the previous version of ICD, there is a very, very poor representation of rare disease in it. So 20 years ago, we start to reference that in orphanet database, and then around I think it was 10 years ago now, we also provide an ontology dedicated to that. So we did the orphanet rare disease ontology, especially to have a place to describe those type of concepts which are not described anywhere else. And so yeah, the legacy is really important. And I think there is a lot of different things between the clinical and the research field as well, and the application ontology that also depends on the context and the usage of that. So I think it's quite a never-ending story in a sense, and that's why we end up also with KRSM nowadays and things like that, because it ends up at the end, even if we have a lot of standards, including packets or even a lot of different type of things, at the end you still lack some kind of representation, especially in some special fields such as the rare disease. So I think there is a lot of rooms for improvement at the level of different ontologies and clinical terminologies providers, but our aim is also to have the ability to bridge between the different spaces, and I think there is a topic on that during the biohackathon also as well. I think that the next level will be also to ease this mapping in more automated way, using a lot of machine learning technologies and so on to ease a bit the process, because one of the good things with the ontology is to be sure that from a meaning point of view, you are no more ambiguous, let's say. So that really helps to leverage the interoperability from semantic level.
See, I agree with all of that. Just to highlight that Alberto touched on a very important issue. That's the purpose, right? These things should be fit for purpose. We have. Not go into the details of the definition of ontology, because it's a lost cause anyway. But if you consider all these things that try to provide some further information about the meaning of things, if you call those ontologies, we see all these artifacts that are being produced. Many of them have very different purposes. A lot of the things that are produced by the linked data, Semantic Web communities, for instance, they are meant to be a way for computational systems to reach common identifiers for concepts that are understood by humans, right? Once the humans assign a type for something, an identifier for something, then the machines can start connecting. Some other ontologies are meant for semantic clarification. And then we need a different type, it's not only a different technique on how to define this, but a different set of tools to do that. We need different languages, description logic-based languages themselves are not enough for us to express everything that we need to express in this level of abstraction. So we need something else. And in this case, even things that are described and put in a PDF file, if the purpose is for people to agree on what this thing actually means and how these things relate to each other, that will be sufficient, right? Of course, it's not sufficient if you want the machines to start operating on that. But that's a different purpose that needs different techniques, different tools, and so forth. I think that my point here is that we have to be clear what we want these things for, so we can choose the proper, what are the good enough ontologies for that purpose, and not other ones, the different tools and techniques to be used.
I have a logistic question. We do have time on the calendar, but is it okay if we go to wrap up? Because we're also needed for some other things. Is that okay? So if yeah, and so do I, because I just wanted to how do you say that? Is it celebrate the right word? In relation to what Louis was saying, one thing that I was really pleased about, what Mark and your team observed when we were doing at the start, before starting this core model, is the notion that what seems to be in common with a lot of the data that we're dealing with is that they were measured and that there was a measurement process that led to a value out of that measurement process. This is a common pattern that we see again and again and again in most of our data, and capturing that in this model is something that is very common. So there we can perhaps, in annotating what exactly it is we're measuring, there we probably have all the issues that Luis was alluding to, but that it was a process that led to a measurement with value coming out of it, that I think we can reasonably well agree on, that's something we most of our data, most of our experimental and medical data relates to. So I just want to also applaud you for that, because I think that's very useful.
Thanks, Marco. I have 2 microphones. Yeah, to wrap up, this is ironic coming from a person that titled his tutorial Integrating and Acting with a Network of FDP of Fair Resources. I wanted to think about what this session ended up being. We gave a tutorial on how to implement. Yeah, sorry. So that was dense, and you can simply follow instructions, follow implementations, specifications, but then the session devolved into us thinking about how to use these things, right? Because we have tools, but we have to think how to use them, for what purpose. And that's the one of the main points of verification. The first and most important step is defining objectives for verifying your data. So that's everything I wanted to say.
Thank you.